plotting a graph is something we do quite often in physics, and there's a lot of things to remember when you do it. So this video is going to go through how to do it properly. So what are the things we have to remember? Draw points, lines and axes neatly using a sharp pencil. We use a pencil so that if you make a mistake you can rub it out and start again, and it needs to be a sharp pencil so that your points are accurate. Axes must go up in sensible steps of 2, 5, 10, 20, 50, 100, etc. Not in 3s or 9s or 7s or things like that. That means each big square, or if you've chosen it, each of the half squares here, should be really a 2 or a 5 or a 10 or some multiple like that. Choose your axis scales so that the points cover at least half the graph paper. You don't want your graph just tucked into one corner, and you don't want it a line across the top. It should be as much as you can filling the paper. Label both the axes, so the x and y axes have to have a quantity and a unit. Draw the points accurately with a neat cross. If it's clearly a line graph, then you draw a straight line of best fit with a ruler. And if it's clearly a curved line, then you carefully draw the best smooth curve you can by hand. You need to decide by looking at the points whether it should be a straight line or a curve. If it says a line of best fit, that could still be a curve or a straight line. And if it's a straight line, you use a ruler, and if it's a curve, you go by hand. We'll look a bit more detail of how to do that later. So let's have a go at plotting one of these and see how we get on. Question 1. A student investigates the distance travelled by a snail. Plot a graph of the distance travelled on the y-axis against time on the x-axis. Now, just in case you have difficulty remembering which is which, the way to remember it, x is a cross, so it's across, and y is the other axis. So we have y up and x across, like that. Okay, before we start putting pencil to paper, the most important thing is choosing what axis scales we use. This is probably going to take you quite a while. Don't rush it. We have to make sure that these numbers fit on our axes, but we need to make sure they go up in sensible steps, and we need to make sure they cover half the graph paper. So let's see what scales we should use. So on the x-axis, we need to go from 5 up to 30. And on the y-axis we need to cover from 3 up to 17.8. So these numbers aren't really suitable for using, but we need to fit those in somehow. Now, if the number at the bottom is a lot smaller than the number at the top, like less than a quarter the size of the number at the top, then really you should take it down to the origin, because there's no point stopping before the origin. But if these were quite close together, you don't have to put the origin in. Okay, so both of these we should probably start from 0, okay, because these numbers are quite small. But 17.8, that's not one of these sorts of numbers. We need to cover 17.8, but we need to maybe go up to about 18 or maybe 20. So let's think that we may want to go up to 20. 30 looks like it might be a sensible number. It's a nice round number. 17.8 wasn't a round number, so we need to go to another round number above that, which is sensible. So let's see, 0 to 20 on that axis, 0 to 30 on this axis. Let's see if we can fit it in this way round. There's nothing to stop you changing it to go the other way round if you want. And you don't have to start a little way in. You can have your axes along the edges if you want, as long as there's a bit of paper there. The reason is, on an exam, they will actually print the graph paper on the paper, so you're going to have plenty of room around the outside. So we need to go from 0 to 30. Well, if we go in 2s, that's going to be 2, 4, 6, 8. That's clearly too small. Let's go up in 5s. 0, 5, 10, 15, 20, 25, 30. That actually fits quite nicely. If we went up in 10s, 10, 20, 30, that's not filling half the paper. So it looks as if a large square being 5 would be good. The other side, going up the y-axis, we're going to go from 0 to 20. Let's see what we can fit. 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, actually, we don't have to go to 20 because 18 will fit. Okay, well, 17.8. So although I said 20 here, we could take it up to 18, and that happens to fit. So 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. That fits really nicely. So let's draw those axes in. So we've got the axes with the numbers on. The bit that's missing from our axes is the labels with quantity and unit. So that's the other thing we should put in first. Again, I haven't drawn any points yet. I'm just concentrating on the axes. So the x-axis was time in seconds. So it's time in seconds. And the y-axis was distance travelled in centimetres. So distance in centimetres. Now what I have to do is plot those points. So I take the first point, I've got 5 seconds and I have 3 centimetres. So I have to start from the 5 and I go up to where it says 3.0 centimetres. Well, each half big square is actually 1 centimetre, so I can easily plot the decimal points. So it's 3.0, so 5 is here, 3 is here. That's my first point. Second point, 10 seconds, go up to 6.2, 6. Each small tiny square is actually 0.2, so that's 6.2. If we do the rest of them, 8.8, 20 is 12.0, 25 is 15.2, 17.8, which is there. So that's all my points plotted. Now, how do we tell whether that's a curve or a straight line? Well, one of the easiest ways is to turn your paper kind of diagonally, so you're looking along it like that, and see whether the points look as if they line up mostly. Slightly wiggly, but they're mostly in a straight line. They're definitely not in a curve, so I'm going to take that as being a straight line. That means I have to plot a best fit line with a ruler. Now your best fit line, if it's a straight line, it doesn't have to go through all the points. It also doesn't have to go through the origin. It may not, but it should go close as you can to the points. You're looking for even spread either side of the line. Going here would be too many that side. Going here would be too many this side. So I have to go somewhere in the middle and plot a line which is straight. So I've got 1 point this side of the line, another point that side, another point just slightly this side. That one's on the line, that one's that side, that one's this side. So it's a fairly even spread. And that's my graph plotted. I don't have to put a title. It's not usually something that comes up in an exam, but if you want to, you can. So let's have a go at the second question. A student investigates the extension of a spring. Plot a graph of force on the y-axis against extension on the x-axis. Force is going from 1 to 6. The extension, we've got these actual experimental results, but then they've given us the mean. So the only one we plot is the mean. We don't plot these values. So what scale do we need? On the y-axis, we're plotting the force. Okay, and that needs to go from 1 up to 6. And on the x-axis, we need to go from 10 up to 60. Now, again, 10 is less than about a quarter of 60, so we should probably start from 0. 1 is less than a quarter of 6, so we should probably start from 0 there. So we need to go from 0 to 60 and 0 to 6. So it could be pretty much the same scale, it's just multiplied by 10. So let's see what will fit. Okay, so let's turn it around this way so I've got a little bit of space. Okay, so if I take 0 here and I go up in 1, 2, 3, 4, 5, 6, that would fit if I multiplied by 10. So that'd be 10, 20, 30, 40, 50, 60 would fit. And going up this way, let's see, 2, 4, 6, 8, 10, 12, no, 1, 2, 3, 4, 5, 6 would take us up to there. If I tried to make it any bigger, it doesn't fit. If I went up in halves, so if that was half 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, doesn't fit. And this is at least half the scale. So I'm going to go 0 to 6 up here and 0 to 60 along here. Okay, so let's plot those in. So I'm going up in tens, 0, 10, 60, and I'm going up in ones here to 6. I could plot 7, but there's no point. Next thing, I need to remember to label them. So this axis is the mean extension. So it's extension in millimeters. On the y-axis, I've got the force in newtons. Okay, so let's plot the values. We haven't got one at 0, but we've got 1 newton, okay, is 10 millimeters. Okay, so 1 newton, 10 millimeters. 2 newtons, 20 millimeters. 3 newtons is 31 millimeters. 5 is 51, and 6 is 60. Okay, and again, let's look along it. it's basically a straight line. Okay, so we're going to draw our line through it, and again we need to try and make points even either side. One thing we don't do, we don't join them dot to dot. Okay, we are allowed to extend them beyond the point. I know in biology they don't let you do that, but this is physics, and we actually want the points to go, the graph to go beyond the points, so that we can see what would happen at 0 or at higher numbers. So let's turn over and have a go at the third one. Okay, police camera records the speed of a car as it comes to a stop. Plot a graph of speed against time, with time on the x-axis. So time is going along the bottom, speed is going up the side. We need time to go from 0 up to 14, and the speed has to go from 35 to 0. Starting at 0 here, 2, 4, 6, 8, 10, 12, 14 just fits. 5, 10, 15, 20, 25, 30, 35. That fits as well. If I went up in 2s, 2, 4, 6, 8, 10, 12, 14, 16, that doesn't fit. And if I go up in 10s, 10, 20, 30, that's too small. Okay, so 5s fits quite nicely up that way, and 2s fits quite nicely across the bottom. Time in seconds axis, 35, and this is the speed in meters per second. Okay, so at 0 time, we're at 35.0 meters per second, so that's there. At 2 seconds, we're at 29.9, 29 will be there. 29.9 is close to 30. Can't plot it exactly, but I can see that it's just below the 30. 25 is there, 24.8 is about there. 10 is 9.8, which is just below 10. 4.8, which is just below 5. And 14 is 0, which just fits on the corner there. Looks very much like a straight line to me. So we draw our best fit line with the ruler, trying to get it as close as possible to the points, but not necessarily through exactly. Just for this one, I'm going to put a title on. Okay, but we don't have to do that. I don't think it's ever worth any marks in an exam. Final question, question 4. Physics teacher measures the rate of cooling of his cup of tea during break time. Plot a graph of temperature against time. Okay, so let's use the back of this graph. Now, this one we have y-axis is going to be temperature. X-axis is time, so the time has to go from 0 to 9. And the temperature has to go from, well, 82 is the highest, down to 23. Now, 23 is still quite a high value. We don't have to go down to 0, okay? It might be sensible to go down to 0, but we don't actually have to. It might be easier to fit it in if it doesn't. Let's start with the x-axis first. So 0 to 9 has to fit. Let's see if we get that. So let's go up in ones first. So 0, 1, 2, 3, 4, 5, 6 doesn't fit. Let's go up in 2s. 0, 2, 4, 6, 8, 10. That fits quite nicely. And in fact, it fits quite nicely, and I'm going to start from 0 here, because then I'll do 0, 2, 4, 6, 8, 10. That will fit quite nicely if I start with 0 there. Okay, 23 up to 82. Well, let's make it round numbers nearby. So if we started at 20 and we need to go up to 85, that's the next sensible looking round numbers above it and below it. Well, 20, go up to 85, we'd have to go in steps of 5, wouldn't we? So let's try that. 20, then 25, 30, 35, 40, 45, 50, 55, 60, 65. That doesn't fit. Okay, so the next one up would be 10s. So we could go up in 10. So 20, 30, 40, 50, 60, 70, 80, 90 would fit. But actually, if we went up to 90, we've got 2 spare squares. We could start from 0. So we could do 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. And that would fit. So that's my axes planned. Okay, so the only reason I've gone up here rather than here is that I can fit the x-axis in by doing that, and it just gives me a bit more space here. So let's draw in the x-axis first. It starts from 0, and I was going to go up in 2s, wasn't I? So 2, 4 minutes. Going up this axis, I'm going to start from 0. I didn't have to, but it fits quite nicely. So I'm going to start from 0 and go up in 10s. 10, 20. Okay, and that axis is the temperature in degrees C. So at 0 minutes, we have 82 degrees. So that's 82. 1 minute is 64. 1 minute is 64. 5 minutes is 32, 24, 23. Now, let's look along that. If we look along that, that definitely doesn't look like a straight line. Okay, you can see it's definitely curving. If you plotted a straight line, or tried to plot a straight line, all your points at each end are one side of the line, all your points in the middle are the other side, which makes it look as if it's definitely not a straight line. So this time we have to draw it as a curve. The curve is going to be going that way. If I draw it with my hand this side, I have to kind of push against the curve to make it draw properly. A much easier way is if you have it this way round and your hand is on the inside, then your hand will automatically curve like that and you can make a smoother curve. What we're looking for is a nice confident curve in one stroke. It doesn't have to hit exactly the points, but it should go as close as you can. We're not trying to make it shaded. Okay, that looks dreadful if you do that. We're trying to make a single smooth curve. So you have to do your best to try and do confident curve. Let's have a go. Okay, and you can see that as I was doing it, I was able to use my hand as a pivot to produce that curve. And it doesn't look too bad, I don't think. That was a first go. It's worth practicing that at home before you actually get to a graph. It doesn't have to fit exactly to the points. It needs to be fairly close, but it needs to be a nice confident curve. And that is my cooling curve. So cup of tea cooling down. Okay, and that's my title. So there's a few graphs plotted, and you can see that one of the most important things is getting the scale right at the beginning. Spend a bit of time on it. Think it through before you put your pencil on the paper. Go through step by step, thinking going up in 2s, going up in 5s, going up in 10s. See whether your values will fit before you actually plot the graph.